In this video we look at more integrals involving exponential functions. Remember that the basic indefinite integral for b raised to the x is 1 over natural log of b times b raised to the x plus c. B has to be a number here. If we can write an expression so it fits this exponential form, we can apply this rule. In our first example, let's look at the indefinite integral of 3 to the x times pi to the x. Using laws of exponents, we can rewrite this as the indefinite integral of quantity 3 pi raised to the x. Now this fits the pattern of the basic rule for b raised to the x with b equals 3 pi. The final answer is 1 over natural log of 3 pi times 3 pi raised to the x plus c. Now let's look at the indefinite integral of x times e to the negative x squared. Here there is no algebraic way to simplify. Let's try substitution with w equals negative x squared. Solving for our substitution parts, we get dw dx equals negative 2x, and solving with algebra we get dw equals dx over negative 2x. As we plug in, we get x times e to the w times 1 over negative 2x times dw. The x in front of the e to the w and the x in the denominator cancel, giving the indefinite integral of e to the w times negative 1/2 dw. We pull the negative 1/2 in front to get 1/2 times the indefinite integral of e to the w dw, which we know is 1/2 times e to the w plus c. Plugging back in w equals negative x squared, we get negative 1/2 times e to x squared plus c. The next integral looks similar but turns out to be very different. Here we have the indefinite integral of e raised to the negative x squared. We might try algebra or substitution here, but it turns out that neither one will work. Even though this indefinite integral looks pretty similar to the last one, it turns out that mathematicians can prove there is no way to come up with an answer using only basic or elementary functions. There are actually lots of problems like this in math, which look simple but turn out to actually be impossible to do, regardless of how good one is at math. What if we change the problem slightly to look at the definite integral from 1 to 3 of e raised to the negative x squared? This problem is different because now we're looking at a definite integral instead of an indefinite one. We can't use the fundamental theorem of calculus for this problem because, like we just talked about, we can't find an antiderivative. However, we can use a computer to approximate the answer. Let's do that. Going to Desmos, I define f of x as e raised to the negative x squared. Then I type int and set the bounds of integration. The computer tells me that this area is approximately 0.1393832. If I just needed an approximate answer, this is good enough. If we look at the graph of e raised to the negative x squared and shade the area corresponding to this definite integral, we see that it's pretty small. So this small number seems very reasonable. The important thing to remember here is that a definite integral corresponds to an area, so you can approximate that area in different ways. Let's look at another example, which is cosine of e to the x multiplied by e to the x dx. Here we try substitution with w equals e to the x. When we take dw dx, we get e to the x. Then we solve for dx and get dw over e to the x. When we plug these pieces back in, things cancel nicely to give us the indefinite integral of e to the w dw. Using the basic antiderivative rule, this is sine of w plus c. When we plug back in w equals e to the x, this becomes sine of e to the x plus c. This would be our final answer. Now what if instead, we had a definite integral, like the definite integral from 2 to 5 of cosine of e to the x times e to the x dx. Here it's possible to use the fundamental theorem of calculus, because we can find an antiderivative. In fact, just a second ago we found that the antiderivative was sine of e to the x. So applying the fundamental theorem of calculus gives sine of e to the 5 minus sine of e to the 2. This is an exact answer, though you could approximate it if you want. Now let's look at another similar problem. What if we had the indefinite integral of just cosine of e to the x? We might try substitution again with w equals e to the x. Then we take dw dx equals e to the x and solve until we have dx equals dw over e to the x. When we plug in the pieces, this becomes cosine of w times dw over e to the x. This is a problem, because I have mismatched terms where some variables are w and some variables are x. This won't work. We can't use the substitution for w here. Let's try it with Wolfram alpha here. Notice that Wolfram alpha also can't find an answer in terms of basic elementary functions, because there isn't one. Instead we are given the answer in terms of a series expansion. You will see much more about series expansions later in the course. So what if we had the definite integral with this function, something like the definite integral from 1.3 to 2.1 of cosine of e to the x? Because this is a definite integral, It represents an area and we can use a computer program to numerically approximate that area. Typing this into Wolfram Alpha gives that this area is approximately 0.192543. That's a pretty small area, because there's both positive and negative signed area in this curve.